call is now being recorded.
All right. So in the last class, we saw right the Poisson approximation, and we saw using that how we could analyze the coupon collector problem better, right? Tighter analysis, and then we said that so we studied balls and bins and related problems as a abstraction of the hashing problem, right? Where you have a set of elements and you want to hash them into a table where such that you can compute the hash function easily as well as find an element. Sorry.
Citizens was a priority and celebrations could be held later as well. Maharashtra.
I'm sorry about that. Yeah. So yeah, so that so we were studying this hashing problem. So and where you have a set of elements from a universe which you want to store so that you can do membership easily, right? And we said that if you want to store m elements, then you need log m bits per element if you want to do the find operations correctly, because you need to uniquely identify the elements, correct? And what we're going to see now is a data structure which is going to somehow overcome this space bound, right? We are going to it's going to enable us to store elements in much smaller space per element, but then the answers that we give will not be always correct. Okay, and so this data structure is called a Bloom filter. It's been around since the 1970s, and the name is because of this Bloom, the person who came up with this data structure. So as the name suggests, it's something like a filter. Say for instance, you can think of like a spam filter, right? Where what you have is you want a way to get only the correct uh, emails into your inbox, right? You have you want to create a rule so that only the correct emails get into your inbox, but you're okay if a few spam mails do get it, right? You don't want to miss out on any of the actual mails, but then you are okay if, say, in a week 1 or 2 spam mails come in, right? You can always delete that, right? So that is the sort of data structure that we are going to construct, right? So you want to construct you are going to do membership again, where for every element in that set we need to answer correctly whether that is in the set or not. But for elements that are not in the set, it is okay to give a wrong answer once in a while, right? So it's going to give, just like a spam filter, it's going to have false positives, right? So in the case of spam filter, what it means that occasionally a spam gets into your inbox. That's what you mean by so it's like a filter. It's like a first level in a, say, a multi-level hashing or something, right? You want to say that certain elements are there in the set or not. Whenever it's in the set, you need to answer correctly. If it is not in the set, it's occasionally you can make a mistake, right? So that's what that we are going to construct, right? So you have it. You can think of it as an approximate set membership problem, correct? And the nice thing is that it requires less space in the hash table per item, correct? So this is what we will do, right? So what the idea of a Bloom filter is that instead of actually storing an element, right? So the core idea is the following: you basically, instead of storing the element, store an indicator bit, uh, for an element. Right, you're going to construct a function which is going to map every element to a position in this array, but instead of saving that element there, you just put indicate saying that this corresponding element is there. Right, so if you actually ask for membership of the correct element, you will go to that bit and see that bit is 1, and you will say that that element is present. But unfortunately, if there is an element that is not in the set, it is still possible that your function will map it to one of the elements in this array where there is a 1, but you have no way to know whether it is the actual element or some other element, in which case you might give a wrong answer. Right, so that is the idea of a Bloom filter. Okay, so then so the thing is, if you just have one bit per item, it might be that you can make the error might be large. So what you instead do is the following. Right, what you do is you choose, so say you have so here is the setting. Right, you have a set S, okay, coming from some universe U, such that the cardinality of the set S is equal to M. Okay, and you have an array where you're going to store this. Right, this array A is your Bloom, the data structure of length N. Okay, what you do is you take K, we'll fix what K is, K hash functions, call them H1, H2, so on till Hk. They are, you can assume that for now that they are random hash functions, random functions. Okay, ideal random functions. Right, our analysis will all, we are going to assume that these are ideal random functions. So you have K hash functions, and the way you store these items is as follows. Right, for every I in S, okay, you set the bits A of H1i, A of H2i, and so on till A of Hki to be equal to 1. Right, so you're somehow building in some sort of redundancy into your system. Right, so what you do is you set these k bits in the array to be 1. Right, and there the bits are obtained from the hash functions h1 to hk. Okay, so this is the initial step. So this is how you store, this is the way to store the set S. Right, so this is your data structure. You want to set check membership in S. So S is stored in this way. It's stored in an n-length array using k hash functions. Right? So one thing you can notice here is that k times m is greater than n. Right? M is the size of the array, size of the set S. K is the number of hash functions. We'll assume that km is greater than sorry, n is greater than km. So it's a large enough array so that you can store everything, right? So we'll assume this for now. Correct. Yeah. All right. So then, so this is for search storing the elements. Now, how do you search for an element here? Right? How do you search for an element in this array? So given an element I, okay, in the universe, okay, you answer that I is in S if A of H1i equal to A of H2i. All these indices return a 1. Okay, so this is the search process. This is how you search. This is the membership. Correct. You have so you have an element I. You want to know whether I is in S or not. You look at all the indices in A where it could have been possibly mapped by the hash function, and you check whether all of them are 1. In which case you say the element is in the set. Maybe. Yeah. Okay. Any questions so far? Is the data structure clear? Right. It's a fairly straightforward data structure. You just storing some kind of a fingerprint, right, corresponding to every element in the set. Okay. So now the question is, what are the guarantees that you have for this data structure? Correct. So the first thing that you can note is, maybe you can write it as an observation. Right? The first observation is that if I is in S, then the membership testing always gives the correct answer. Right. So the only way there can be an error is, so you only have what are called false positives, right? Which is that there is an I that is not in S, but the data structure returns that I is in S. Correct? These are the only sort of errors that you will have incur in this data structure. And what we want to do is to actually understand, what is the probability, right? What is the uh, probability for false positives? Correct. So far so good. So this is what we are going to analyze. So to analyze this data structure is to understand this quantity, right? So how do we go about analyzing this, right? So what is it that we want to know? So when do we answer correctly for an I not in S? The only way that you can answer correctly, right? The only way that you will say that I is not in S is if you actually look at H1I, H2I, and HKI, you actually find a zero, right? So for an I not in S, you will answer correctly if there exists a J such that HJFI is equal to 0. Sorry, A of HJFI is equal to 0. There is some index where it is a 0, right? So so if you notice, for a fixed I not in S, the probability for a false probability that you will say I is in S depends on the number of zeros in this array, right? The only way that can happen is if, so notice that these edges are purely random functions. So the mapping of edge, mapping of I to a index by edge is purely random. So therefore, the probability for getting a wrong answer, right, or probability of answering correctly depends on the fraction of zeros in this array, right? So with that in mind, let's ask this question, right? So if so, say you map all the elements of S into A. Okay, you do all this. So fix let J be a index in I. What is the probability that A of J is equal to 0? What is this probability? Right? You map all the elements of S into A and set the corresponding bit. Now you take a fixed element bit in the array. What is the probability that A of J is equal to 0? In this case, I think you can give a exact answer. Approximate is also okay, but you can probably give the exact answer also. What is this value? 1 minus 1 over n to the mk, right? So the way I think Sathik would have got this is take one element, right? Fix an element, right? So if you want to say fix an I in S, right? Um, so the probability that say h1 of I is equal to j is 1 over n, correct? Similarly, probability of h2 of I is equal to j is also 1 over n. So if you want a of j to be 0, then what you want is that every hi, every hash function maps I to a index other than j, right? So there are k hash functions. So the probability is 1 minus 1 over n, 1 over n to the k, right? So this is for a fixed I in S. There are m elements in S. So the probability that all of them are going somewhere, this is something like 1 minus 1 over n to the k, right? So if you notice, this is approximately e power minus km over n, right? Or by our approximation as n tends to infinity, right? So this is the probability that a particular bin is actually 0. A bit is actually 0, correct? So what are we interested in? So we want, so let z be the fraction of zeros in the array A. Okay. Now for a fixed, this is what we want. For a fixed I in, not in S, what is the probability that uh, I is a false positive? What is this value? What is this probability? If Z is a fraction of zeros in the array. Yeah, 1 minus Z to the K, right? Because what do you want? You want, so if you take a function hi, right? Take a hash function say hj, right? You want it's a false positive if hj maps I to all the edges map I to a point that is not a 0, right? So I is a false positive if this happens for every hi. So there are k hash functions. So with probability 1 minus z, the first hash function maps it to a bit that is not 0, right? And this is true for all the k hash functions. So in which case this probability is something like 1 minus z to the k, right? This is what we have, right? This is the probability of the false positive. This is what we want to analyze, correct? And what do we know? So we know the expectation of z, right? What is the expectation of z? Expectation of z is just what we have just calculated here, right? The probability that a particular bit is set to 0. So that is nothing but 1 minus 1 over n to the km, right? So in some sense, if you, in some sense, what you can say is that this is like, it's not clear why, but you can say that this is something like 1 minus 1 over n to the km to the k. So why is there a question mark here? Can you tell me? What does this question mark mean? When will this be true? When can you write something like this? What conditions must hold? Right, Z is a random variable, right? So when can you conclude something like this? This is the probability of I being a false positive. When can you conclude this? Or what should be true of Z for this to happen? When is it justified to replace, you know, this with this equation? That's what I'm asking.
Are you asking like the law of large numbers also?
So yeah, so what I'm asking for is some kind of a concentration, right? So you have a random variable Z. I want to replace Z with its expectation, right? That's what I'm doing. So the law of large numbers is specifically for sum of certain by random variables, and you're saying that it is like distributed according to certain other distributions. So see here, what you want to say is that if I want to replace Z with its expectation, you want what I want to know, what I should be sure is that Z is somehow close to the expectation, right? It should be concentrated around the expectation. Then I can say this is something I can replace it this with it's like a high probability bound. I can do this. I know that this is going to happen, right? So what we're going to do now is let's see, let's assume that we can replace it for now, okay, and then we'll see why we can replace it. Okay. Suppose you could replace it for now, then what we have is this: the probability that I is a false positive is given by this equation, right? Which I can sort of write as 1 minus e power minus km divided by n raised to k, right? So now the question is how many, so if the choice of k is with us, we haven't fixed k. So now what we need to do is fix k so that, this quantity is minimized, right? I can choose the k as I want, so that this is minimized. This is your false positive probability, right? I want to choose k so that this is minimized, okay? And this you do standard calculus, right? You can do it yourself and check. You do the differential, you take equate it to 0 and so on, and find what should be the value. And then what you will see is that k will be something like ln 2 n over m ln 2. This is where what the k value is going to be when you try to minimize this quantity, correct? So what it means is, if you want the false positivity rate to be the smallest, then the number of hash functions you need is something like n over m ln 2, okay? And if you substitute this value, uh, so if you notice the number of zeros, right, the fraction of zeros, as we said, what is the fraction of zeros in the array? This we said was something like this was the fraction, right? This is the number, right? The fraction of zeros is like e power minus k km by n. So here, if you substitute k, what you have is something like 1 over 2, right? So in some sense, when you choose so many, if you actually had access to these uniformly random hash functions and you are going to construct a Bloom filter based on that, then your false positivity rate, the probability is going to be like right? So this is 1 over 2, right? So this is 1 over 2 to the n over m ln 2, right? This is your false positivity probability. And if you notice this thing here, right, the fraction of zeros, what does this tell you? This tells you that if you really had, if you were to take these k random functions as your hash functions, then the vector A basically looks like a random vector, right? Because the fraction of A's is like half, which is basically saying that each bit is set to 0 with probability half. That so if you had the purely random functions, then the best scenario that you can have for your Bloom filter, where you have the least false positivity, is when the array looks like a random function, a random string, right? So this is the analysis of the Bloom filter, assuming that this the variable, the fraction of z is indeed like its expectation, right? So this quantity, if you calculate, this is something like yeah. So you can check what is 1 over 2 to the ln 2 and so on, and this is the best that you can have. Right? Two assumptions that we have made, right? The assumptions is the two assumptions that we are making. One is that perfectly random hash functions. And secondly, Z is concentrated around P of Z. Okay. Any questions so far? Any questions? Okay. So we will not worry about this assumption for now, right? The perfectly random hash functions, we'll assume that we have perfectly random hash functions. We will not worry about that. But let's see why this should be true. Right? Let's see why Z should be concentrated around expectation of Z. Okay. So to understand this, let's think about how we would try to go about analyzing this based on whatever tools, whatever we have learned until now in this course. Let's see how one might go about trying to analyze this. Right? So what we know, the strongest sorts of bounds that we know currently are Chernoff bounds. Right? So say you want to apply some kind of Chernoff bound. What you would do is you will say, so Z is this random variable corresponding to the number of zeros. Okay. So one way that I might try to do is that follows. I'll define these random variables Zi, okay, which is one if A of I is equal to 0 and 0 otherwise. Correct. And then I can say the Z is actually summation Zi. Correct. And I could start off from here. So now I have Z is equal to summation Zi. Then I want to know what is the probability that Z minus E of Z is greater than some value. This probability is less than something. Right? This is what I would try to do. Right? And what is where will it fail here? What is the issue that can happen? Why doesn't this work? And say I want to apply Chernoff here. Right? So say Chernoff here. Right? So Zi's are not independent. Right? The Zi's are not independent. How are they not independent? Right? So clearly Zi's are not independent. So you cannot just directly apply Chernoff bounds here because of the fact that Zi's are not independent. And the reason they are not independent, what can you say about why they are not independent? Why do you think they are not independent? Why do you say that ZIs are not independent? What reason would you give? If mk of them are 1, then the others must be 0. Correct. Right. So if I tell you that you know that the ones correspond to the ways in which the hash functions are mapping elements. So if I tell you that so many are 1, then the others must be 0. Right. So if I tell you that certain these random variables, some of these random variables are all 0, which means that the corresponding entries in the arrays are all 1, then you know that the others must be 0, right? Because of the fact that you have this large array and you can't have all zeros, for instance. Right. So in that sense, they are dependent, right? So ZIs are therefore dependent. But they are also dependent in a nice way, just like what Srikanth is saying, right? So what Srikanth is saying is that if I tell you that, say I give you a set of indices, and I tell you that for those indices, Zi is all 0. All of them are 0. Then for the remaining indices, I can tell you that, say that I take a large collection of indices where all for which Zi is equal to 0, right? Then you can basically conclude that in the remaining fraction, the number of zeros must be small. Right? You can't have too many zeros, right? Because you're actually hashing m elements into this array. Right? So if I tell you that there is this collection of indices where all of them are actually 0, then the remaining part cannot have too many zeros. It must be small. Right? So they are dependent in this sort of what is known in a very negative way. Right? So this is formalized using the notion of what is called negative association or negative dependence. Okay? So what it basically trying to say is that if you have a collection of variables, if you take two disjoint subsets, if I tell you that for one subset of these random variables, they all take very large values, then it is going to imply that the other set, the random variables, is going to take smaller values. Okay? So if a random variable has this property, right, a set of random variables have this property, then we say that these random variables are negatively associated. Okay? And in this special case, these ZIs are negatively associated. Okay? We'll formalize the notion of what is negative association. And the nice thing is that if you have a random variable Z that can be expressed as the sum of negatively associated random variables, even if they are dependent, if they are negatively associated, then the Chernoff bound still holds there. Okay? So it's not just that the ZIs have to be independent. Even if they are negatively associated or negatively dependent, even then this statement holds. And what we're going to see is that these random variables corresponding to the zeros in the Bloom filter are actually negatively dependent. Okay. So now let's try to formalize this idea of negative dependence. Okay. So let's see what is negative dependence, and we will prove some properties of these random variables. And then we will show that the number of zeros is indeed Zi is where if these are negatively associated. Okay. So that's what we are going to show next. Okay, so let's formally define what is negative dependence. Is the idea of is the intuition clear of what negative dependence means? Any questions there? Okay. Okay. So let's just define what is called, what they call as negative association. Okay. So we'll say that the random variables x1, x2, so on till xn are negatively associated okay if for all disjoint subsets I comma j of n, right, take any disjoint subset I comma j, and all non-decreasing functions f and g, right? You can say that the expected value of f of xi into g of xj, right? So by xi I mean the set xi I in I is just a shorthand. Similarly, xj is xj xj j in j. Right? These are just shorthands. Okay. So this expectation is at most expectation of f of xi into expectation of g of xj. Okay. So this is the definition of negative association. So we'll say that a set of random variables are negatively associated if for every disjoint subsets I and j, this statement holds. And every disjoint subset and every non-decreasing functions f and j. Right? This is trying to capture the fact that if one of those, if you say that one set is large, then the one set of these random variables take very high values, and the other set must take low values. That's what it's trying to capture. Okay. Any questions on the definition? Okay. So here is some properties that you can notice about these negatively associated random variables. Right? So this is a small lemma that you can see. Right? If so, if x1, x2, so on till xn are negatively associated, then and fi's are non-decreasing functions, then the expected value of the product of fi xi, going from 1 to n, this is at most the product of I equal to 1 to n expectation of fi xi. Right? It's a simple enough observation that just follows from the definition. Right? So you can take so if this is true for every disjoint subset, take one disjoint subset to be the entire set, and the other to be one of those sets, and define the function f. Right? So you can take I to be something like 1, 2 up till n minus 1, j to be the set n, right? And you define you take the function f, which is say product of fi xi I equal to 1 to n minus 1, and g to be the function fn xn, right? And then what you can see is that the expectation of f xi g xn, right? This is at most expectation of f of xi, expectation of fn xn, right? And then this is just inductively continue. Correct? Right? So you can write this way. So in particular, this means that so here is what we can say. This means the following, right? So this is the Chernoff bounds. So if x1, x2 up till xn are negatively associated, and x is the expectation of x, okay, assume that they are identically distributed also, right? And then I'll just write, I don't want to write the bounds, when the then Chernoff bounds hold, okay, the same Chernoff bounds as for independent random variables. Let's assume that these are 0, 1 random variables, okay. So it's as though the same bounds as though they were independent random variables. Same bounds will hold. X is summation xi. Okay. And the proof is also not very hard to see. If you recall how did we do the proof for this? So we had this idea, right? So the proof was to use the moment generating function. So what we did was we said the probability that x is greater than m is same as the probability that e power tx is greater than e power tm, right? And then we use Markov to say that this is the expected value of e power tx, at most e power tx by e power tm. Right? At this point, what we said was that this is nothing but expected value of e power product of e power t xi's, right? I going from 1 to n, right? Divided by e power tm, right? The next step was where we use the independence to bring the expectation inside the product. But now you notice this statement about negatively associated random variables, right? So if you have the function fi on xi's where xi's are negatively associated and fi's are non-decreasing functions, which is the case here for this e power t xi's, then what it means is that I can, instead of an equality, I can say that this is at most the product of I equal to 1 to n, the expectation of e power t xi divided by e power tm, right? So this is the inequality due to negative association. Right? So what this means is that now I can continue. Now what you do is continue the same proof as before. Right? So assuming that these random variables are negatively associated, you can do the same proof for you can say do the same proof for of Chernoff bounds as for independent random variables, and you get the same bounds. Right? So that is very nice because you don't need full dependence, full independence for Chernoff bounds, and you only need that these are negatively dependent. Correct? Any questions so far? Is the notion of negative dependence clear? The definition. Okay. So what we want to show is that I can write z as sum of express sum z as a sum of random variables that are negatively dependent. That is what I want to do, right? So if you recall how we analyze randomized algorithm, typically if you want to understand a random variable, it's we said that in many cases it's hard to analyze that random variable directly. So what we do is we try to split it into simpler random variables and then try to understand their properties and say that even when you combine them, all these nice properties hold for this larger random variable. Okay. And that is what we are going to do here as well. We are going to use some way to look at simpler random variables which we can prove to be negatively associated and how to combine them, right? And to do that, we will look at two properties of negatively associated random variables, which we will then use to show that our random variables corresponding to the zeros are also negatively associated. So the first is what is called the first property, right? Both are not very hard to see. The first is that closure under unions. Okay. So what does it say? It says that if x1, x2, and so on till xn, okay, and y1, y2, and so on till ym are two independent sets of negatively associated random variables. Okay, then the set, the union, the set x1 up till xn, y1 up till ym are also negatively associated. Right? So if you take two independent sets of negatively associated random variables, then their union is also negatively associated. Correct? And how will you to see this? It's not very hard. You basically go to the definition, right? So what you do is say you have two sets I and j, right? So you take two I and j, which are subsets of 1 to n. So this like this n union m, right? Now what you want to say is that you can write I as I1 union I2, where I1 is a subset of these xi's and I2 is a subset of the yi's, right, the corresponding indices. Similarly, j. Correct. Then what do we want to show? You want to show that the expected value of f of, say, I'll call it x1, y1, g x2, y2. Okay. Maybe I'll put a bar here just to. So what is x1 bar? X1 bar is basically the set xi1. Okay. Similarly, y1 bar is the set y I2. Right? So you can look at these two things. Similarly, x2 bar and y2 bar. So you want to show that this is less than or equal to expectation of f of x1 bar, y1 bar times the expectation of g x2 bar, y2 bar. Right? And so the first thing to do is to just write it down in the following way, right? This expectation, I can write it as sum over all these y1 and y2s, right? Where I take the expected value of f of x1 bar, y1 bar, g x2 bar, y2 bar, conditioned on the fact that y1 bar is this string y1 and the y2 bar is a string y2, into the probability that y1 bar is equal to y1 and y2 bar is equal to y2. Right? So you can write it as this using these conditional expectation. And this is nothing but the expected value right, of the expectation of f of x1 bar y1 bar into g x2 bar y2 bar conditioned on y1 bar and y2 bar, right? This is just the standard expectation calculation, right? Because so this you can think of it as a random variable, right? This is a random variable, right? Depending on the choice of y1 and y2, this expectation can take different values depending on that y1 and y2, right? So this is a random variable, so you can write this as a expectation of this quantity. Now what you want to notice is that you can actually apply, so this conditional expectation, right? So here again you can apply the definition of negative association. You can apply the definition of negative association here. Because these xi's and yi's, right, x1 and y1, they are independent. Similarly, x2 and y2. Right? So if you just work it out, expand it out and write, then you will notice that you can write it this way. And then simplifying sufficiently, and you will basically come to this equality. So this I will just leave it for now. If you want, I suggest that you try it. Otherwise, I'll write it down and send it to you if you want to. Right? So it's just some calculation to do, but nothing too complicated. It's just working with these definitions, right? But it's not very hard to believe, at least, right? If you take negatively associated random variables and they are independent, you combine them, then you will again get negatively associated random variables. Right? Any questions on this? Okay. The second property that we will see is again not very hard to see. This is called disjoint monotone aggregation. What does this say? So if you have, if x1, x2, and so on till xn are negatively associated, right? If these are negatively associated, and A is a family of disjoint subsets of n. It's a collection of disjoint subsets. So it's A is something like a collection, say A1, A2 up till AR, such that AI intersection AJ is the empty set for every I comma j in R. Right? If you take such a collection of sets, then look at the random variables f sub a defined on all xi such that I is in A, where A is an element of this collection, script A, right? Such that Fa is non-decreasing. Then these collection of FAs, they are negatively associated. See, notice that these are also random variables now associated. Right? If you have a collection of random variables, and these, if you take a function, then the function of the random variables is another random variables. Now, what you're doing is you're taking independent collection of, you're taking disjoint subsets, and then for them you're defining these functions, and then you get a new set of random variables, and it says that these are also negatively associated. Right? This is again not hard to see, because if you take 2f and g, and you take f of FAs, right? F of FA, that is like taking since FA is non-decreasing and F is also non-decreasing, F of FA is again going to be non-decreasing, and therefore you can apply the same. And since the xi's are themselves negatively associated, you can apply the same definition twice and prove this. Right. So this is again just follows from the definition of negative associativity. Are these two definitions clear? So the reason we need these two nice properties is that we're going to use this to actually show that the zi's that we are working with, the z we can prove negative dependence, negative association using by looking at smaller random variables, right? Simpler random variables. Any questions so far on this? Is this clear? Okay. All right. So then now with these two in hand, I think we have ways to actually show that what we want to prove about the zi's. Okay. So to do that, let's look at instead of looking at the fraction of zeros, let's look at the fraction of ones. Okay. Let x be the fraction of ones in the array A. Okay. I'm going to prove a concentration bound for x. So x I can write as summation xi, I going from 1 to n, right? And I want to show that xi's are negatively associated. Right? Then I can prove the use the Chernoff bound and get a concentration result regarding the expectation of x. Right? And getting the concentration bound for x will give me a concentration bound for z as well, right? Because the fraction of ones plus fraction of zeros is the entire set is equal to 1. Yeah, correct. So let's see why these are negatively associated. Right. So to do that, let's first define a random variable x I comma j comma l. Okay. So this random variable is an indicator random variable. It's 1 if hi of j is equal to l and it is 0 otherwise. Okay. Recall that in the Bloom filter you had these functions h1, h2 up till hk. Right. So xi comma j comma l is 1 if hi of j is equal to l. Right. So when you get j, the ith hash function maps j to the lth bit of the array A. That's what this is. It's 1 if it is the case and 0 otherwise. Okay. Any questions so far? Okay. So now let's fix I. Let's fix I. Okay. Let's fix I and fix j. Right. So recall that j is an element of this S, right, or the universe. You're going to take j from yeah. So j is element of the set S. Let's fix I and j. Let's look at the set of random variables x I comma j comma l, where l is some index from 1 to n. Okay. So the first claim that I want to show is that x I comma j comma l, l in n, is negatively associated. Let's see why this is negatively associated. Right? So what do we want to show? So here is what we want to actually show. Right? So you want to show that if f and g are non-decreasing, right, and you have sets I and j subsets of n such that I intersection j is an empty set, then you want to show that the expectation of f of x I comma j comma capital I times g of x comma small I comma small j comma capital J. Right? This is at most the expectation of f of x with I j capital I times the expectation of g x I x I j capital J. Right? This is what we want to show. Okay. So notice that f and g are non-decreasing, right? And xijls are what sort of functions? They are 0 1 random variables. So they take either 0 or 1, right? So notice that f x I j capital I, this is definitely greater than f with 0 everywhere, right? Because it is non-decreasing. Similarly, g of x I comma j comma capital J is greater than g with all zeros, right? This is because of the fact that these are non-decreasing. Correct? Any questions so far? Is the setup clear? Any questions? Okay. So then I can think of the following functions, right? I look at the function f tilde, okay, comma j comma capital I, which is f of x I j capital I minus f 0 0. Similarly, g tilde as well. Now, the nice thing about these functions is that, so these are non-decreasing for sure, right? These are also non-decreasing. And for moreover, they are non-negative. Right? These functions are non-decreasing and non-negative. Correct? Because of the fact that f was indeed non-decreasing. And the random variables xijls are all 0 1 random variables. Right? Because for every other value that you can put here, it is greater than corresponding to 0. So if f000 is greater than 0, then this is always greater than 0. Otherwise, also this will be positive. Right? If it is negative, then these are only going to be positive. Either if this is negative, then this minus and this is a negative number, which means that it will be positive. So these are definitely non-negative numbers, right? And they are non-decreasing. So now what it means is that to prove this statement, it's sufficient to work with these f tildes and g tildes, which are non-decreasing and non-negative. Right? It is sufficient to prove that it is true for these f tildes. If I prove this statement, then that is sufficient, right? Because f tilde is just f minus f000. This is a constant, right? This is a constant. So if you notice, if you can prove this statement, then that is sufficient, right? This would imply that the corresponding statement here also will hold for any such function, right? Okay, all good so far? So what can you say about this quantity f tilde x I j capital I into g tilde of x I comma j comma capital J? What can you say about this expectation? Right now, you need to use the fact that xijs are xijls are random variables corresponding to the hash function assigning the element j to the ith hash function assigning the element j to the position L. Right? You need to use that. You need to use that knowledge. So, given that and the fact that f tilde and g tilde are non-negative, what can you say about this these quantities? What will be this expectation? So here is another thing, right? So notice the following observation, right? F tilde of 0, 0, 0, 0 and g tilde of 0, 0 and so on till 0 is also 0, right? Because of the definition of f tilde and g tilde, these two statements hold. Right? So then what can you say about the expectation of f tilde times g tilde? Can both these functions be non-zero at the same time? What does it mean to say that both these functions are non-zero at the same time? The question is, can f tilde and g tilde be non-zero at the same time? When you have values being so these values, the random variables are coming from that hashing, right? So yeah, exactly. So as Sarthak is saying, hij cannot be two different values, right? It can only be one value. Right? Hij is has to be some fixed L, which means that what it means is that these random variables, right, xijl, exactly one of these random variables will be 1 and rest everything will be 0 when you take when you look at the corresponding map, right, in the Bloom filter, right? Because j gets mapped to a particular index by the hash function hi. So exactly one of those random variables will be 1, which means that there is no way that you can have both f tilde and g tilde being non-zero, right? At least one of them must be 0. And what does that mean? If in every assignment one of them must be 0, what can you say about the expectation? Right? Expectation itself must be 0. Right? The expectation itself must be 0. Because expectation is just sum of these together with the probability of the corresponding values. And you know that at least one of them must be 0 all the time. Right? Both of them cannot be non-zero at the same time. But this means that, so now you know that, but you know that f tilde and g tilde are non-negative, which means that this is definitely less than or equal to expectation of f tilde x I j capital I times the expectation of g tilde x I j capital J. Right? Because these are non-negative, right? Both these functions are, both these random variables are non-negative. And therefore, there is no way that, this can become 0. This can be less than 0. So this will be at least 0. So that's all that you have to see. So this shows that, this inequality holds. It's based on the observation that this expectation must be 0. Right? Any questions so far? Is this clear? Right? So then, so now what have we shown? We have shown that these sets of random variables are negatively associated, right? But then what we can actually say is that, so you look at the following set, right? You look at x1 xijl where I is from 1 to k, j is from 1 to m, L is from 1 to n, right? So now this is also negatively associated, right? Why? Because of what property? This is these are negatively associated because of closure under union. Right? This uses the fact that this requires the fact that the hash functions HIs are truly random. Right? In the assumption that these hash functions are truly random, these random variables are also negatively associated, right? Because of closure under union. And now, what you do is you look at the following random variable. You look at the random variable x L to be the maximum over I and j I in k, j in m, x I j l. Okay. Look at this random variable. What can you say about this random variable? When is what can you say about this random variable? What values will it take and when? Well, it's a 0 1 random variable for sure, right? It's one if some hash function maps some element to one L, right? So this is one if the corresponding entry AFL is equal to 1. It is 0 otherwise, right? This hash function is one precisely when the entry in that corresponding position, right, in the Bloom filter is 1. That's precisely when it is 1. Okay, and what we can say is that XL is also negatively associated. So the set XL L in N is negatively associated, right? Because of the disjoint monotone aggregation property. Right? Because you have disjoint sets, right? IJL for the different values of L, these are disjoint. And the function that you are having here, the F, the corresponding function is the maximum, right? Which is again non-decreasing, right? As the values of these random variables change, the maximum can only increase, it cannot decrease, right? So therefore, by the fact that if you have a set of negatively associated random variables and you take it the disjoint monotone aggregation, then what you get is again negatively associated. Right? So each of these XLs are negatively associated. And what we are actually interested in, therefore, is X, which is the number of ones in A. This is nothing but the sum of negatively associated random variables XL where L goes from 1 to N. And then you know that then what you can do is this means that you can apply the Chernoff bounds here. Right? So you can apply the Chernoff bounds here. You can say that the number of ones in the array is close to its expectation, and therefore the fraction of ones is close to the expectation, and therefore the fraction of zeros is close to its expectation. So therefore the calculation that we did, assuming that the number of fraction of zeros is actually equal to the expectation, is indeed justified. Right? That is what what we've just shown. Right? And to do that, we have actually shown that these random variables corresponding to the zeros, whether the 0, 1 random variables corresponding to whether a bit is 1 or not in the array, they are dependent, but they are what are called negatively associated. Correct. So that completes this analysis. I think the class, we have also run out of time. So are there any questions here? Any questions? So this is like an algorithm where the data structures, right? The Bloom filter is fairly easy to describe, and to get a tight analysis, it requires a lot more newer tools than what we already saw. Right? It's not that easy, right? You need to understand the properties of the random variables involved and analyze it very carefully. There are other ways to analyze this as well, because these random variables have some other properties also. They are not just negatively dependent. They have some other properties and which you can use. But this is one analysis of it. Yeah. Any questions so far regarding today's lecture? Okay. So then I think we'll stop for now. We'll continue tomorrow. So what we will do now is that, so till now we have done analysis assuming perfect random hash functions, but that is not always the case. You cannot, it's not possible to have truly random hash functions, right? That's too idealistic. The analysis works, but what we will see now is how do you work when you don't have perfectly random hash functions, right? What properties, how do you construct hash functions which are not purely random, but which are efficient to construct and which are efficient to store, which is what we need finally in our algorithms. That is what we are going to see tomorrow. Okay. So if there are no more questions, I think we'll stop for now. Okay. Thank you.